In this video, I'm going to finish up the Fundamental Theorem of Calculus. So this is the Fundamental Theorem of Calculus, Part 2. Part 2. First thing we need to do, or you need to do, is to remember the intermediate value theorem, which says basically if you've got a nice, pretty continuous function on an interval, somewhere in between there's a number that the derivative at that point will equal the slope between the two endpoints of the curve. Okay, let me do a picture, show you what this looks like in English. So suppose we have this curve, nice, smooth, pretty curve, no pointies, no holes. Now, the line between the two endpoints is this blue dotted line. I can find another line tangent to this curve and parallel to that line right there. If I drop a perpendicular down, that's my C. So that's the C I'm looking for. So f prime of C is equal to the slope of this blue line between A, f of A, B, f of B. So how am I going to use this? Well, let's look at this. Remember this? It's in your nightmares. We want to add up all these boxes. And we came up with the limit and the shortcut and all that stuff. We had A was the first one, so this can be thought of as x sub 0. B is the last one. This can be thought of as x sub n. The difference between the two was delta x, and it's the same delta every time. Remember I emphasized that you could use the left endpoint, you could use the right endpoint, you could use the midpoint. You can use any point in between these two to determine the height of the rectangle to get an estimate. And when you take the limit, if it's integrable, you'll get the same answer as if you use the left, the right, the middle, the fourth one, whatever. I'm going to consider, let big F of x be any antiderivative of little f of x, and I want you to look at f of b minus f of a, which can be rewritten as f of x sub n minus f of x sub 0. Why are you doing this, Megan? I know you're asking that question. It's like, what are you doing? Well, this is a proof. I'm going to sneak a proof in on you. And proofs are typically come out of nowhere because somebody's worked on this thing for ages. They've got it just perfect, just right. And so it looks like they pulled it out of their ass, when really they've got lots of paper somewhere that they've roughed up, or, written on to figure out the answer. So just go with it. So I have f of xn minus f of x0. And I'm going to do something weird. I'm going to add 0 a bunch of times. And I'm going to add 0 in the form of f of x sub n minus 1, a negative 1, and a positive 1. These two together make a 0. And the next two, this is so long, it ran off that's better. It fits all on the page. But it still looks gross. Who wants to write all that shit out? So we're going to use our summation notation, which is the whole point of learning this. So we can have a nice, shorter way of saying it. Now, between any one of these, so this is f of x sub I and f of x sub I minus 1. Between any x sub I and I star, I can find a point xi star where the derivative, the big f of x derivative, is the slope between those two endpoints. So I have f star of I, put it in the derivative, I get the same as this crap. So let's go to the next page so I have more elbow room. So we're here. Now, but this looks familiar. This is delta x. So rearranging this equation, I have f prime of x star I times delta x equals f of x I minus I'm getting tired of reading that. This. But the derivative of big F is little f. So what we have is f of x star I delta x is f of xi, big F of xi minus big F of xi minus 1. Now this should start looking familiar. So that means, okay, go back to what we know. Yeah, let's go to this thing. So I can plug this in for this because they're equal. So what I have now is f of b minus f of a, because that's where I started with, is equal to the summation as I goes from 1 to n of little f of xi star delta x. Now I'm going to take the limit of both sides. I'm going to take the limit as n goes to infinity. Now on this side, which is my left, on the left side, there are no n's there. So as n goes to infinity, these guys don't give a shit. So they're just going to stay f of b minus f of a. On the right, I have the limit as n goes to infinity, which we know is the integral. So that's the big deal. I now know that the integral from a to b of f of x dx is equal to big F of b minus big F of a, where big F is any antiderivative of little f of x. Now, any antiderivative means we could say whatever we came up with, plus 5 or plus 7 or minus pi. We tend to just ignore the plus c because it's going to subtract off anyway. So let's look at what we can do with this. Suppose I want to integrate 4x cubed minus 3x squared plus 2x from 1 to 2. Now, if I had to do it with the summation and the limit, this would always be so hard. My xi would be 1 plus my delta would be 1 over n. I have many summations. I'd have to cube that thing out and square it. Oh, gross. But thanks to the fundamental theorem of calculus, all I have to do is find an antiderivative, which is x to the fourth minus x cubed plus x squared. I do this notation because I need to plug in f of a and then f of 1, little big get. So I do this one step at a time so I don't get confused. So now I stick 2 into this thing and then 1 in and find the difference. Usually I don't put this much information in, but put the 2 in, the 1, and your answer is 12. Oh, that was a whole lot easier, wasn't it, than the summations? Integral from 0 to 1 of f 5x minus 5 to the x dx. Ooh, y'all don't like those integrals. Integrating this, I get 5x squared over 2 minus 5 to the x over natural log of 5, taken from 0 to 1. If I stick a 1 in here, I get 5 halves minus 5 over natural log of 5, minus, if I stick a 0 in here, this becomes 0, and this becomes 5 to the 0 is 1 over natural log of 5. That should actually be a plus, because you have a negative negative. I made a mistake. So assume you. But on the next line, I correct myself. So 5 minus a negative 1, negative 5 plus 1, I get a 4 over that. So see, that's not too bad. So we're going to practice some of these. So we're going to go back to finding antiderivatives and some gross antiderivatives, but not too gross. I'll wait till after the test when we get into really, really snarky ones. And that is the fundamental theorem of calculus in a big old nutshell. He's saying goodbye. And if anybody can tell me, help me figure out how to make him say wave as a animation, I'd appreciate it. Thanks.